Hey guys, Chris here from Adapt Tuition, and in this video I'm going to show you how to perform multiplication with matrices. Alright guys, before we go any further, I just want to give you a heads up. Where I am located right now, there's some construction going on right outside my door. So if you guys hear any extra noise, I am really sorry about that, but I have absolutely no control over that noise. So please bear with me. Also, before we go any further, if you have not had any experience or exposure to matrices before this video, you don't know what a matrix is or any of that stuff, I have another video on matrices that explains all of the basics. So I want to suggest you to take a look at it. I'm going to put a link in the description below. So take a look at that video, and when you're ready, come back and watch this video. If you have already been exposed to matrices and you're ready to tackle multiplication, then let's begin. Before we can multiply two matrices together, we need to determine whether or not they are compatible for multiplication. To do so, we need to compare the orders of the two matrices involved. Let's take a look. Okay, so recall that the order of a matrix is simply a reference to the number of rows in that matrix and the number of columns in that, oops, I spelled that wrong, the number of columns in that matrix, with the number of rows being cited first and the number of columns being cited second. Rows are lines of numbers that run horizontally in a matrix. In this first matrix, I have 2 rows. Columns are lines of numbers that run vertically. In that first matrix, I have 2 rows and I have 2 columns. So it's referred to as a 2 by 2 matrix. In this second matrix, I have 2 lines of numbers that run horizontally, and I have 3 lines of numbers that run vertically, which means that's a 2 by 3 matrix. And in this last matrix here, I have 3 lines of numbers running horizontally and 2 lines of numbers running vertically, which means this is a 3 by 2 matrix. The reason we need to compare the orders of the matrices together to know if the two matrices are compatible for multiplication is because the way we combine the elements in the matrices is a bit different than with addition and subtraction. Let's take a look at addition very quickly. Okay, so when we are adding two matrices together, first of all, they need to be of the same order. So I've just gone with two 2 by 2 matrices here for the sake of simplicity. And when we add the elements in two matrices together, we are adding the corresponding elements, which means this is the first element in the first column in that matrix, which matches or corresponds with that element there. So we'll add those 2 elements together. Similarly, this is the second element in the first row, second element in the first row in that matrix, so we're combining those 2 elements together. Further, this is the first element in the second row in that matrix, that's the corresponding element in the second matrix. So we're going to be adding those 2 items together. This is the bottom right one, second element in the second row and second column. Same thing here. So basically we're adding the elements once they're in the same relative positions in the respective matrices. 1 and 5 will give us 6, 2 and 6 will give us 8, 3 and 7 is 10, 4 and 8 is 12. Okay, so when we're multiplying matrices, the way we combine elements is a bit different. We actually have to multiply entire rows in the first matrix by entire columns in the second matrix. And how we do it is we have to multiply the corresponding elements of the elements in the row in the first matrix. So first element in the row by first element in the column. And then second element in the row by second element in the column. And so on. Right? And then we actually have to add up all those products together. So for two matrices to be compatible for multiplication, the number of elements in the row of the matrix of the first matrix must be equal to the number of elements in the column in the second matrix. So let's take a look at a very easy way to determine that before we start multiplying matrices together. And we're also going to take a look at a little tip to see what the order of the resulting matrix will be. So we'll know what the resulting matrix will look like before we even get to it. Okay. So the short way to know if two matrices are compatible for multiplication is to compare their order. So let's take one matrix A, which has order R1, C1, and let's take matrix B, which has order R2 and C2. If the number of columns in the first matrix is equal to the number of rows in the second matrix, then these two matrices can be multiplied together. And the order of the resulting matrix will be the number of rows from the first matrix versus the number of columns from the second matrix. Okay, so what I'm going to do now is I'm going to go through several examples to show you exactly how to multiply two matrices together. And what I want to suggest is that you get a pen or a pencil and a piece of paper or somewhere to write down these examples and try them as we go along. Of course, for the first couple, I have to show you what to do. So after that, get a pen and piece of paper, write down the examples, go through them, because we learn by seeing, we learn by hearing, but we learn by doing most of all. Okay? And if you still have any questions, please feel free to put them in the comment section below. Okay, let's get it. Okay, so in this first example, I have two matrices. This first matrix has one line of items going across, and you have two columns in that matrix. So that is actually a 1 by 2 matrix. In this second matrix, I have two lines of items going across. Even though it's only one element in each row, an element is still considered to be either, it can be an entire column or an entire row. So we have two rows going across, and we have one column going down. So that is a 2 by 1 matrix. So what was the test? If the number of columns in the first matrix is equal to the number of rows in the second matrix, then we can multiply those two matrices together. See how happy it looks? Okay, and the resulting matrix will have an order of that many rows and that many columns. So we're actually only going to have one number, or one element rather, in this matrix when we multiply these elements together. Now let's see how this looks. Okay, so we're going to have to multiply the entire row by the entire column, but we're multiplying the corresponding elements in the row by the corresponding elements in the column. What do I mean by that? Well, this is the first element in the row, and that's the first element in the column. So we have to multiply those two together. And then we have to add the product of, well, this is the second element in the row, and this is the second element in the column. So we have to multiply those two things together. All right, so 1 by 3 will give us 3, 2 by 4 will give us 8, and 8 and 3 will give us 11. So that's, by the way, a 1 by 1 matrix. Okay, so once again, we had to multiply the entire row by the entire column, and more specifically, we had to multiply the corresponding elements in the row, as you can see with the colors, by the colorful ticks, by the respective elements. We multiplied those corresponding elements together, and we added those products together like so. Okay, so that's the first example. Let's get on to the second one. Okay, so in this example, I have two other matrices here. And in the first matrix, I have one row and two columns, which means that that is a 1 by 2 matrix. That's the order of that matrix. In the second matrix, I have two lines going across two rows, and I have two columns going down, which means that that is a 2 by 2 matrix. So, are these matrices compatible for multiplication? How do we know? If the number of columns in the first matrix is equal to the number of rows in the second matrix, then yeah, we can multiply them together. And what will the order of the resulting matrix be? Well, it will have that many rows and that many columns. So we're going to get back a 1 by 2 matrix. So it's going to look like that. Now, in the previous example, we had a 1 by 2 and a 2 by 1. And that gave us back a 1 by 1. So a 1 by 2 will have one row and two columns, which means we're going to have one element here and one element here. Now, how does this work? I mean, well, let's take a look. Let's just jump in, all right? So remember, we have to multiply the entire row by the entire column, and that's going to give us one element. And we have to multiply the corresponding elements in the row together. So that's 1 by 3, and we have to add the product of the other pair of corresponding elements in, well, between row and column there. So that's going to give us 2 by 5. Okay, now let's take off some ticks there. So we can do it again for the next column. So the next column, we have to multiply the same entire row by the entire column, and we multiply the corresponding elements. So we're going to have the 1 by 4 being multiplied together. Oh, sorry, that doesn't look too good. And we have to add to that the product of the other pair of corresponding elements. Right? So the green ticks are by the first elements in the respective row and column, and the purple ticks are by the second elements in the row and column. So that's, sorry, 2 by 6. Almost forgot to put the working. Oh, let me make those brackets a little more even. Right? 1 by 3 will give us 3, 2 by 5 is 10. 1 by 4 is 4, 2 by 6 is 12. 3 and 10 will give us 13. 4 and 12 will give us 16. And is that a 1 by 2? Yes, it's a 1 by 2. All right, great. So in this example, I have a 2 by 2 matrix, and this is a 2 by 1 matrix. So the question is, are they compatible for multiplication? Well, the number of columns here is equal to the number of rows here, so yes. And the order of the resulting matrix will be a 2 by 1, which means it's going to look basically like that. Okay, so let's get the colors going again. Okay, so first row by column. First element in the row by first element in the column, that'll give us 1 by 5. And we have to add to that second element in the row by the second element in the column, which will give us 2 by 6. All right, let's take off those ticks so we could do the second row by column. So now, once again, we're doing this row by this column. So that's going to give us the bottom, the elements in the bottom row in that matrix there. So first element in the row by first element in the column, that's going to give us 3 by 5. And then we have to do the second element in the row by the second element in the column. And that's going to give us 4 by 6. So let's simplify now. 1 by 5 will give us 5. 2 by 6 is 12. 3 by 5 is 15. Sorry, that doesn't look like a good 5, right? And 4 by 6 will give us 24. So our resulting matrix will be 5 and 12 is 17. 15 and 24 is 39. Is that a 2 by 1? Yeah, you have 2 rows and 1 column. Okay, so in this example, we have two 2 by 2 matrices. So we can clearly see that the number of rows is equal to the number of columns between the two matrices. Number of columns here is equal to the number of rows, and the resulting matrix will be the same 2 by 2 order. Now let's see what happens here. So let's get our colors going again. So first row by first column. So first element in the row by first element in the column. So that's 1 by 5 plus second element in the row by second element in the column. 2 by 7. All right, let's get those out. Now what we're going to do is we're going to go across to populate where that element will eventually be. So once again, now it's the first row by the second column. So let's go. So first element in that row by first element in that column, that'll give us 1 by 6. And then we're going to go with the second element in that row by the second element in that column, which will give us 2 by 8. All right, so we see we're multiplying entire rows by entire columns, and we multiply the elements as we go along, the corresponding elements. Okay, so now we're going to do second row and first column. Now, any time multiplying by the second row, you're going to have elements in the second row in the resulting matrix. All right, so let's go. We have first element in the row by first element in the column, which gives us 3. Oh, oops, that's plenty of noise there. All right, 3 by 5 plus, and now we're going to go second element in the row by second element in the column, which is 4 by 7. All right, cool. Let's take this off. And now we have one more set of row and column to go, which is this same last second row and second column now. So let's go. First element in that row, first element in that column. That'll give us 3 by 6. Plus now, second element in the row by second element in the column, 4 by 8. Okay, so we've done the hard work. Oops, I took out one of the elements. So let's proceed from here. Actually, I wanted to go across because there's something I want to show you guys that's very important afterwards. So if we get this stuff done, 1 by 5 is 5 and 2 by 7 is 14. So we have 5 plus 14 there. 1 by 6 is 6 and 2 by 8 is 16. So we have 6 plus 16. 3 by 5 is 15, 4 by 7 is 28. So we have 15 plus 28. Sorry about the noise. And then we have 3 by 6 and 4 by 8. So that's going to be 18 plus 32. All right. So 5 and 14 will give us 19. 6 and 16 is 22. 15 and 28 is 43. 18 and 32 is 50. And that is a 2 by 2 matrix. Okay, so what I want to show you guys now is something important, which is this thing here. Matrix multiplication is not commutative. Commutative, the commutative property applies to regular addition, regular multiplication. 1 plus 2 is 3, as is 2 plus 1. The order in which the terms appear didn't matter. Normally with multiplication, let's say we had 2 by 3, that would be equal to 3 by 2. The order in which the terms appear doesn't matter. With matrix multiplication, however, that is not the case. Now there is a notable exception to this, which I will get to in another video, a different video, but not this one. So what I'm going to do, I'm going to let this matrix here be A and this matrix be B, and I'm now going to multiply. I'm going to reverse the order of the multiplication. So now I have 5, 6, 7, 8 multiplied by 1, 2, 3, 4. So this is matrix A, this is matrix B and matrix A. Okay, so let's go. So now we're doing first row by first column. Okay, so let's go with 5 by 1 plus 6 by 3. And now let's go once again first row but second column now. Okay, so that's 5 by 2 plus 6 by 4. Okay, lovely. Now we're going below. So we're going second row, first column. My bad. Let's get rid of that one there. Okay, so we have 7 by 1 plus 8 by 3. And now we're going to go second row, second column. So that's 7 multiplied by 2 plus 8 multiplied by 4. Now even from right here, we could compare the products and the sums. They're not the same. So even from right there, we get a feel for the fact that these matrices are not going to give us the same final answer. But let's finish working. So 5 by 1 is 5, 6 by 3 is 18, right? Which of course does not correspond to that. Now we have this next piece here, 5 by 2 and 6 by 4. 5 by 2 is 10, 6 by 4 is 24. Down here now, 7 by 1 is 7, 8 by 3 is 24 as well. 7 by 2 is 14, 8 by 4 is 32. 5 and 18 will give us 23, 10 and 24 is 34. 7 and 4 is 31, 14 and 32 is actually 46. And these two are not equal to each other. So once again, just to drive home the point, matrix multiplication does not conform to the commutative law. The order in which the matrices are multiplied does matter. Right? They will A multiplied by B will not give you the same as B multiplied by A. As I said, there's one exception to that, which I will cover in a future video. Okay, so now I want to talk about matrix multiplication and the associative law. The associative law has to do with grouping things together and do we get the same answer or not. So basically, if I were to multiply these three matrices together, A multiplied by B multiplied by C, how the answer, I can get this, I'd have to go sequentially. I'd have to multiply A by B first and then multiply by C. Interestingly enough, I get the same answer as if I multiply A by the product of B and C. Now, I am going to show you guys how this works. But of course, I'm going to save some time because if you notice, the two matrices that I brought here are the same two from before. So I already have an answer for matrix A by B, the product of A by B. So I'm just going to skip back to that page. I'm going to pull this 19, 22, 43, 50. So 19, 22, 43, and 50. And I'm going to multiply it by C, which is equal to 3, 1, 4, 1. Right? First four digits of pi. Okay, so of course we have some slightly bigger numbers than as per usual because we have a pre-existing product, but that's okay. We don't run away from big numbers just because they're big. Okay, so let's go. So we have first row by first column. So we have 19 multiplied by 3 plus 22 multiplied by 4. And now we're going to do same first row, but now by second column. So that's going to give me, whoops, I forgot to put back on that pen. That's going to give me 19 by 1 plus 22 by 1. Some easy numbers there, right? Let's go to the second row. Second row, first column. So the product there is going to be 43 by 3 plus 50 by 4. And finally, we have same second row by second column. Right, so that's, once again, easy stuff. 43 by 1 plus
50 by 1. Okay, so 19 by 3 will give us 57, 22 by 4 will give us 88. 19 by 1 is 19, 22 by 1 is 22. Right? One is called the identity of multiplication because when you multiply by 1, you get back the same number. 43 by 3 is 129, 50 by 4 is 200. 43 by 1 is 43, 50 by 1 is 50. 57 and 88, I believe, is 145. You can correct me if I'm wrong. 19 and 22 is 41. 129 and 200 will give us 329. 43 and 50 will give us 93. Okay, so now in order to prove the remainder of what I need, I'm going to need to have the product BC. Right, so I just did a bit of movie magic there, and I organized that, these two products, these two matrices written down here, so you wouldn't have to wait and see me write it out. Okay, so let's get into multiplying those two together. So let's do first row by first column. So 5 by 3 plus 6 by 4. And then first row by second column. 5 by 1 plus 6 by 1. Now let's do second row by first column. So 7 by 3 plus 8 by 4. And then 7 by 1 plus 8 by 1. Okay, let's proceed from there. 5 by 3 is 15. 6 by 4 is 24. 5 by 1 is 5. 6 by 1 is 6. 7 by 3 is 21. 8 by 4 is 32. And then we're going to get 7. Sorry, I have a multiply sign here, and that should actually be addition. And 8 by 1 is just 8. Okay, 15 and 24 is 39. 5 and 6 is 11. 21 and 32 will give us 53. And 7 and 8 is 15. Okay, so we have one more product to do, which is multiplying A by this matrix we just found. All right, so we have A multiplied by BC to do. Let's get that done. Okay, so first row by first column. So we have 1 by 39 being added to 2 by 53. Then first row by second column. So we have 1 by 11 plus 2 by 15. Then we have second row back by first column. So we have 3 by 39 plus 4 by 53. And second row, second column, 3 by 11 plus 4 by 15. Okay, 1 by 39 will give us 39. 2 by 53 is 106. 1 by 11 is 11. 2 by 15 is 30. 3 by 39, I believe, will give us 117. 4 by 53 will give us 212. 3 by 11 is 33, and 4 by 15 is, no, not 30. 4 by 15 is 60, as a matter of fact. When we add 39 and 106, we get 145. 11 and 30 is 41. 117 and 212 is 329. And 33 and 60 is 93. Now let's see if that corresponds to this matrix up here. Well, look at that. 145, 41, 30, 329, and 93. So once again, matrix multiplication, while it doesn't conform to the commutative law, we can actually apply the associative law. So we could group together the products if we are multiplying more than two matrices consecutively. And if you have, as you saw me do, if you have an answer from previous, you don't need to go and rework that product again, because as you can see, it's a lot of work. Okay guys, just a couple more things to do and we're going to be all free and clear with this matrix multiplication. Okay, so here, what I want to show you guys is the square of a 2 by 2 matrix. The first thing I want to point out is what the square is not, right? So if I wanted to do a squared, this would not be equal to simply squaring the individual elements inside of the matrix. No. When we square something in maths, we multiply it by itself. So if you want a matrix A squared, the matrix product A squared, you have to multiply A by A, which means you have to multiply 1, 2, 3, 4 by itself. 1, 2, 3, 4. All right, so I'll do this very quickly. First row, first column. 1 by 1 is 1. 2 by 3 is 6. Now this is how some people do it. They multiply as they go along, right? Now we'll go first row, second column again. So 1 by 2 is 2 and 2 by 4 is 8. Now second row, first column, 3 by 1 is 3 and 4 by 3 is 12. And second row, second column, 3 by 2 is 6, 4 by 4 is 16, which will give us 7, 10, 15, and 22, which is definitely not going to be equal to if we just squared the elements of the original matrix. All right, so once again, when you square a 2 by 2 matrix or square any matrix that you can square, don't just square the individual elements on the inside. Multiply the matrix by itself. In some cases you will be able to, and in some cases you will not be able to. Okay, so the final batch of examples I'm going to do for you guys will involve non-2 by 2 matrices, because a lot of times the most popular type of matrix you will see is a 2 by 2 matrix by a 2 by 2 matrix. But it's quite possible for them to bring other types of the matrices of other orders for you to multiply together. So let's take a quick look at just a couple of examples, because the principles of how to multiply two matrices together don't change. Okay, so firstly, let's get this one going. So here we have 2 rows and 3 columns, which means the order of that matrix is 2 by 3. This one, we have 3 rows and 1 column, which means we have a 3 by 1 matrix. These two numbers are equal, therefore we can multiply them, and the resulting matrix will be a 2 by 1 matrix. Let's take a look and see how this will turn out. So we're going to do first row by first column. Well, only column as a matter of fact. So first element in the row by first element in the column. So we have 1 by 7 plus second element in the row, second element in the column. That's going to be 2, oops, sorry, 1 second. It's going to be 2 multiplied by 8 plus, and then finally we have third element in the row by third element in the column, which will give us 3 by 9. All right, so let's get rid of those ticks so we could repeat that for the bottom row. Okay, so going on the bottom row now, we have the first element in the row by the first element in the column, which will give us 4 by 7. Then we could take the second element in the row and multiply by the second element in the column, which will give us 5 by 8. And then we could take the third element in the row by the third element in the column, which is 6 by 9. Okay, let's see how this turns out. 1 by 7 is 7, 2 by 8 is 16, 3 by 9 is 27. 4 by 7 is 28, 5 by 8 is 40, 6 by 9 is 54. 7 and 16 is 23, 23 and 27 is 50. 28 and 40 is 68, 68 and 54 I believe is 122. 68, yeah. All right, so that's that example. Okay, so for our final example, we have these two matrices. Now, the first one is a column matrix because it's just a single column with multiple elements, multiple rows. And this is a row matrix because it's just a single row with multiple columns. And you might be asking, well, how can we multiply these two together? It doesn't look like it's compatible. They don't look like they're compatible with each other for multiplication. What do? We assess the orders of the matrices. So this matrix has 3 rows and 1 column. What's wrong with me? And this one has 3 columns and 1 row. So, 1 row and 3 columns. So these two numbers are compatible, are equal, which means that the matrices are compatible for multiplication. And the order of the resulting matrix will be a 3 by 3. How is that even possible? Well, let's take a look. Remember what I said earlier. A single element could be an entire row, and a single element could be an entire column. So that's exactly how this is going to play out. So if we go row by row, so row by column, so what that means is that we're just going to get 1 by 4. And if we go again now with row by column, that's the second column. So we're not going to be adding that product of 1 by 5 to this 1 by 4 because it's an entirely different column. Right? Remember, in the previous examples, even if this one up here, we we added the 2 by 8 and the 3 by 9 to the 1 by 7 because 7, 8, and 9 were in the same column. With this matrix down here, there's only one element in each column. So that means that the 1 by 5 will take the place in the middle, and then the 1 by 6 will go to the third column. And then we're just going to repeat with the next two numbers. So this row will be multiplied by this column, then this column, then this column. So we're going to get 2 by 4, 2 by 5, and 2 by 6. And of course, finally, we're going to have one more row, which is the 3 multiplied by each of these columns. So we're going to do 3 by 4, 3 by 5, and then 3 by 6. So all that's really going to happen is that this matrix is basically going to be scaled up to 3 rows, and each row is going to be basically a multiple of the first row. The first row will just be 4, 5, 6, as we saw initially. Then we're going to have 8, 10, 12, and then we're going to have 12, 15, and 18.
All right, so that was a lot. But that's basically it for matrix multiplication at the CSEC level. I will be doing future videos on this topic that will cover the inverse of a 2 by 2 matrix and how we can use matrices to solve simultaneous equations. Interesting stuff. Okay, so if you found this video helpful, I would really appreciate it if you give that like button a hit. And if you're finding the content on this channel helpful to you, then please feel free to subscribe and be sure to click that notification bell so you can be notified every time I release a new video. Okay guys, thanks for watching. I'll see you next time.